Hello, I'm Beatriz. I'm going to talk about in-situ experiments. We do a lot of that, but our users do it. We help them a little bit. And I hope you get to appreciate how useful they are and learn about your sample. So why would we do in-situ experiments, and what is that? Well, when we control any of these parameters during the experiments, or any other, say light, pressure, temperature, gas, atmosphere, mechanical stress or strain, voltage or current. Let's say we have a battery. So we're measuring our X-ray diffraction patterns, and at the same time we are controlling one of or more of these parameters. And this is because we want to learn about the structure of the material, or what it's doing, what it's supposed to do. Let's say if it's a battery, we're going to bring our battery cycler and cycle it back and forth and see how the structure changes. So we're doing the characterization. And this is the property tetrahedron is showing that all these structure, properties, performance, processing, they're all interrelated in a material. And you change one and you're likely to change the others. So we're going to do our characterization and learn about the structure, which is about with X-rays, which is about the most important thing that you want to know about a material. And this has many applications in several fields that are very trendy recently, which we're very proud to help our users in. To control these parameters, say temperature, we have 4 different furnaces. This is our battery cycler for the battery experiments. We have many users coming, and we plug this in and cycle the battery back and forth. Well, that's another furnace we have. This is a stress rig for tension and compression that we recently bought and we are commissioning to make it available for the users. This is another little furnace that Adam and Joel came up to study in-situ cement setting. And finding out what phases go on and off during the curing of cement state. This is a cryostat for experiments down to 10 Kelvin. This is another stress rig, and I'll show an example of a group up from Jiu-Su that brought it here, and they did experiments on the tension and compression too. And there are more, and sometimes some in-situ setups we have, sometimes the users bring their own, and we help them design their in-situ setup to be compatible with our stations and meet their needs. We see an example of a professor here that studies materials for solar cells, and he has a very customized setup for his experiments. And these experiments, they're quite efficient to do here because we are in a synchrotron. And the brilliance of our source, which is flux in also considering the divergence, flux per millimeter square per milliradian square. So the brilliance, the synchrotrons are much more brilliant than regular home diffractometers. So we have more flux in a very small spot, meaning that we can measure really fast and have high temporal resolution. And then we can see fast changes in the samples, well, because we capture very fast. And that has, well, many applications that we will see some. We'll see phase transitions, which XRD is ideal for. See, this has application in microelectronics, batteries, solar cells, mechanical applications, catalysis, corrosion, high pressure, and you name it. I'll have a few examples within my time frame. And this is a demo experiment that we did at the lower energy wheeler beamline XRD station with potassium nitrate, and this has a phase transition from orthorhombic to trigonal when we increase the temperature 120, 140 degrees C. You can see very nicely in XRD, the phase change. And for temperature control, okay, I mentioned we have several options. Cryostat, this is a cryojet that goes down to 80 Kelvin, this one 10 Kelvin. This one goes close to 1,000 degrees, and this is a similar version of this. And I talk about a tight relation between structure and property, and the steels are a stark example of that. We have different phases that we can find in steels: austenite, martensite, epsilon, or alpha. And they can have very similar compositions, but the structure is different, and their properties to corrosion, formable, ductile, austenitic steel is very good in this, but martensitic steel then is good for wear resistant, is harder, stronger. So, and it's just because one is FCC and the other is BCC. It makes a big difference. But then how do you do if you want a steel that is good for both? Like we want a steel that has the best of both worlds. But some smart people have come up with a smart processing. And again, remember one of the corners here is the processing. A smart processing called quenching and partitioning, attempting to get the best of both worlds in between austenite and martensite steels. And quenching and partitioning consists of a heat treatment. They heat the austenitic steel to red hot, very hot, and then they quench it quickly, getting the transformation of part of this austenite to martensite. And then they heat it just a little bit to allow the carbons to move from the martensite to the austenite, and that's going to make the composite here more stable. And then you end up with a steel that has a good balance of high tensile strength and good elongation. So this is an example of how you can influence material properties with the processing. And we have a group in Toronto, might be familiar to some, who came here. Oh, sorry, this is a group from Finland. So they were interested in getting insights about this quenching and partitioning processing. So they took our furnace and put the samples there, and they're going to use high energy X-rays from the higher energy Wheeler beamline and measure in our large area detector. It's about 40 by 40 centimeters. Here are the Weisserrer rings. And they're going to do the diffraction experiments during the thermal processing of the steel samples. This is similar to the quenching and partitioning thermal process. And the diffraction patterns, they change very nicely as they heat and cool, and you can see how the martensite phase shows up and austenite, and everything falls together because they know a lot. And they put this also together with DFT, density functional theory calculations. And when they do that, they get details about the microstructural evolution of their steel. They get details about the mechanism phase transformations going in the sample, and they get to elucidate how the carbon diffuses in there from martensite to austenite and which energy barriers they are. And eventually they come up with a steel that has better properties. That's the final goal. You get to understand how something works, and then you're in a better position to make it better. And then we get a paper that we're proud of, or a patent. That'd be better. So that's an example. I'm moving to another example now in microelectronics. We have a station from IBM in the lower energy Wheeler beamline that you might remember. It looks about like this. This is the station here. It's very crowded, but it has a diffractometer, the Huber diffractometer. They use it to characterize thin films, but microelectronic materials are full of thin films, very, very small dimensions. And they can do rapid thermal annealing up to 1,000 degrees. And there's lots of annealings in the processing and construction of microelectronics chips. So, and they need to know how stable those structures are, how if there are changes, they need to know the reversibility, they need to know when it will break. And so this station, it also has a high purity helium and nitrogen, and it has a 4-point resistance probe, which is important in microelectronics, and it has optical light scattering for the roughness. So we're measuring resistance, roughness, and changing the temperature in ultra-high purity atmospheres while we're doing X-ray diffraction and getting the structural changes of this material. And this is completely automated with trays for samples and a robot. They operate from New York most of the time, but it's open for users. And this is the sample chamber. And if you're ever interested, this is the format of the sample holder. And this is the sample fits here. Very small, usually silicon or germanium substrate with thin films that we want to learn about. And I brought, well, this is a video of the station in operation. Let's see if I can make it. It's a video that needs updating. The station is operational, even though it says future here. So there's the robot. This is the IBM team. That's the sample chamber opened. There's the sample. This is a heater. It's water cooled, so it won't melt when we go to 1,000 degrees. So now, so this is a pneumatic system that's gonna grab the chamber lid and unlock and open the chamber. Here's where the sample goes, and the robot's gonna come and grab the sample, and it's gonna check with a little sensor that is actually has a sample on the grid, and yeah, it does, and it's gonna put it here. And this pneumatic system is gonna come and close the chamber. And there's a LabVIEW visual interface to control the experiment and program long sequence of experiments that you can run from anywhere. So we're moving to the next slide. So what can we do with this station? They can investigate different growth conditions for their thin films. They can get better nucleation processes, improved film stability, try to get lower interface roughness. This is an example of nickel monosilicide films versus temperature. You can see how when they heat up, you start with nickel and silicon, but eventually you get the nickel silicide phase and then a different one. And you can also see at the same time how the resistance is changing and how the roughness is changing. So this is a material that's important for the CMOS devices. There's another example here, metal nitride barriers for ruthenium interconnect. So they're trying to find alternative materials, alternative to copper for interconnect applications. So in this case, they have the silicon substrate and a metal nitride barrier, and then the ruthenium. And they're gonna heat this up and see how resistant it is, how much can they heat it before it breaks. So they're heating it at different ramp rates and checking the different phases that show up. And at about, depending on the ramp rate, there's a temperature when that interlayer of metal nitride is going to break, and you will start seeing the ruthenium silicide phase. And that's when it breaks and they get activation energies, and they get to know how, when how much can they hit before it breaks. So one last example that I brought for this station is an application for phase memory materials research. And a phase memory material is a material that's going to change something, in this case, the resistance, when it goes from one phase to the other. And germanium telluride is one of those materials when it's in the amorphous phase, it has a very high resistance. And when it's in the crystalline phase, it has a very low resistance. So you can use that for a non-volatile memory chip. And they are going to research this germanium telluride with different concentrations of niobium. Is this niobium? I hope so. SB. Antimony. Yeah, niobium is MB, sorry. Antimony. So they're going to check how different concentrations of antimony, interesting, are going to affect the speed, the crystallization speed of the germanium telluride. And here's the amorphous phase, has no peaks. It has a very high resistivity, which we're measuring at the same time. And when you heat up, you get the crystallization, and then the crystalline phase has very low resistance. And that's how you distinguish in a phase memory chip the two states. And this is reversible, and it can be read with a small voltage that is not going to change the amorphous to crystalline or back. And with these experiments, they are finding different factors. They are finding the speed, the crystallization speed, which is an important parameter in these materials. They are finding the crystallization temperature, the resistance, the thermal stability. They get a wealth of information. And they found the best concentration of the SB in this case. So that's the last example I brought about the IBM station. I have some battery examples here, which is increasingly popular. And we have many batteries, probably only in this room and everywhere. And we would love that they work at -50 one day for a long time. And this is a photo in the high energy Wheeler beamline of our battery setup. Here's a pouch cell commercial battery connected to our battery cycler. And we have our large area detector here. The X-rays come from this yellow hole here. This way, it goes through the sample because we're talking about high energy X-rays with very good penetration. And we're going to record the XRD pattern of that battery while we charge and discharge. And you can see both the anode and the cathode materials. They're changing as you charge and discharge. So we can follow these structural changes and learn about what's going on in there and come up, but hopefully eventually come up with a better battery. And this is a user we have in Alberta. He comes with his customized battery setup, and he puts it first in the lower energy Wheeler beamline, then in the undulator beamline. So that thing has a structure of a battery here with different layers and electrodes and lithium. And he puts that all together in our diffractometer. We shine the X-rays at a grazing angle, and we cycle that. And he gets, different phases of different materials. This is aluminum, lithium in a wide variety of phases. Then he can learn about his battery. And soon publish something. Oh, this is a professor from the university here, Tim Kelly, and this is another customized sample environment, particular for his solar cell materials. So in a solar cell, we want to control the light. He has a lamp. We want to control temperature and humidity. So all of that is controlled in this chamber, which is also compatible with our diffractometer in the Wheeler beamline and in the undulator beamline. So he puts his candidate material for solar cell in here. We control everything, all these parameters, and we do XRD and find out about the phases and find out if it's good, when it's going to break, and try to make it better. So this is an example of putting the light on and off. The different phases show up. And in this particular study, he was trying to find the failure mechanism for his cells in a humid environment, because there's humidity, even though it might not be ideal for the solar cells. They have to live in a real world. So he can come up with better materials. Oh, next topic. I'll be quick about this, corrosion. But corrosion is a big deal, and it's very costly. Things can break, and they're expensive to replace. Countries can spend around 3% of the gross national product fixing things. That's just because they're corroding. And that's billions of dollars in our countries. So if we can get a better hold of that and better materials that corrode less, that is a jackpot. So this group was going to investigate the corrosion mechanism of 4-series stainless steel. So, and they use a furnace with a controlled gas environment. So they try to put an atmosphere that is similar to the atmosphere around us. We have oxygen and water and nitrogen, and they're going to subject this sample at a temperature cycle. Depending on the application, we have to survive. And they're going to see what happens with X-ray diffraction. And here's the composition of this stainless steel. And stainless steel, well, is mostly iron, and it's stainless because it has chromium. So chromium forms a chromium oxide layer in the surface, is what makes stainless steel stainless. So there's a protective chromium oxide layer, and they're going to heat their sample in this atmosphere and see what's going on and how it breaks and why. And as they do their temperature cycle, they can see several phases coming on and off. And they arrive to the conclusion that the original chromium oxide layer starts, there's iron diffusing into it and getting less and less chromium, and there's more iron, and then eventually on the surface you end up with iron oxide, and your chromium layer is depleted, and there's no more protection. And well, that's how they explain the breakaway of this stainless steel. No stainless anymore. And one last topic, because we're getting to the half-an-hour mark. And this is about in-situ mechanical testing. And there's many in-situ rigs that you can use, depending on where you go and your application. This one was in Brazil. This one is in England, in Diamond Synchrotron. This one's at the APS. We bought this one, and we hope to have it available next year. This is one, a tiny coin-sized stress rig that one of our users brings to the undulator beamline. And here it is mounted on the undulator beamline. The controller is so small that it fits the cryostat. So he can do mechanical test and tensile and compressive experiments. Here's the sample. That tiny thing here is the sample. And this is the size of a coin, right? So he puts his single crystal, their hair-like sample, puts it inside a cryostat, and he can do the tensile experiments and measure the XRD at the same time, down to 20 kelvins. And I'm going to show an example. This is from a group in Toronto. We have some students from that group here. And they're investigating a very hot topic, hot from several sides, because it's related to additive manufacturing, which is an emerging technology where you can do very intricate shapes of materials. And they are growing materials that are high entropy alloys, so 5 or more elements in very similar concentrations, forming a high entropy alloy. So that's a widely broad compositional space for alloy design that will get you better materials. And here is a representation of their 3D printer, and they go doing layer by layer, depositing their sample. And in this particular case, the microscopy shows the layer different phases. And out of this stick, they're gonna cut 3 samples, one parallel to the deposition direction, one inclined, and one perpendicular. And they're gonna see how the mechanical properties depend on the direction of these layers. The anisotropy will influence the mechanical properties. But how? We're gonna get these 3 sticks, parallel, inclined, and perpendicular, and put it in the stress rig, canvas-wise, about this size stress rig that they bring here. We attach to our station and pull that sample until it breaks while measuring X-ray diffraction patterns. So here's the X-ray beam coming, and they're stretching the sample with no care in this work. And here are the diffraction patterns in our large area detector. And we can see how the many phases transitioning and changing and new phases showing up. And they can draw conclusions about strengthening mechanisms, work hardening, fracture behavior, and they can see how the anisotropy in the sample influences these mechanical properties of the materials. I'm approaching the half-an-hour mark. I'll quickly mention that there are many examples in catalysis, and catalysts are very important. They are everywhere for almost every synthesis around. They are very present in refineries and in our cars and like everywhere. And we have this little cell where we control temperature and gas, which usually catalysts operate at high temperatures in hazardous atmospheres. It's my very realistic representation of X-rays hitting the sample and the detector on the back. And again, properties and structure are very interrelated. And this is a gold catalyst showing how the nanoparticle size is key to have strong catalytic properties. If you have small nanoparticles, there'll be high catalytic activity. At the moment they grow, the catalytic activity is gone. So it's very important to control the gold nanoparticle size. And this group, they come up with a very good catalyst by avoiding the migration of the gold nanoparticles. They migrate. If you hit it too much, they're going to migrate and coalesce and grow, and there goes the catalytic activity. So I will quickly wrap up and reach the conclusions. In-Situ experiments give you a whole lot of information about your sample on their working conditions. You want to make better materials with a certain application in mind. You can come up with what do you want to control during your measurement. Is it temperature? Is it gas? Is it stress or strain or current? And apply that during your experiment, and try to come up with a better material in the next iteration. Thank you.
I have a very short question. Is it possible for you? You said you're talking about the controlled gas and temperature also. Is it possible to do this in-situ analysis for a compound under high temperature and under a specific gas? For example, argon, nitrogen, ammonia, blah, blah, blah. Is it possible for you to do it?
Yes. We can either do it in the capillary cell that we will show here. Let me see, that one. The gas comes here, comes on one end and goes out on the other end. And these are resistance, so you can hit it. And the IBM station, it has You can go to 1,000 degrees and ultra high purity only. So if you want to go dirty toxic gases, you'll use this one. Yes. Oh, sorry, he was first. Yes.
So it's very interesting to know about in-situ experiments. So I was just wondering if do we have anything just like us analyze sensing sort of thing, like where we can inject analytes and check for any biosensors, like with biosensors in situ.
Inject something that I don't know if I understood the question. The closest thing I've done when I've done catalytic experiments, you come in with, let's say, CO, and I have a mass spectrometer on the output, and I can see what gases are on the output after the initial gas went through the catalyst material. I haven't done that yet, but it's possible.
Something like the samples inside the capillary and
Yes.
the analytes in the injection and inject.
What are you injecting?
Like the analytes to check like how the biosensors changing, the properties are changing with analytes.
It could be possible. I don't know.
I think I think we understand. We already discussed. Yeah, maybe. I was just wondering if we have anything.
We can talk about it. As I said, the users come with their specific needs, and we can potentially come up with a solution for your specific case. So yes,
What's the highest pressure you can work with?
we have diamond angle cells that I didn't show here, but they can go to, there's a large variation, but I think 20 gigapascal, I think.
20 gigapascals?
Yeah, I think so.
It's pretty big.
Yeah.
Now the samples are tiny because there's two diamonds that you press. There's a gasket like a washer in the middle, and you put that in between the copper structure, and you crank up the screws, squishing that gasket, and the sample is in the little hole, and then you just you put a ruby there to know what's the pressure, because ruby has fluorescence that you can that shifts with the pressure.
Oh,
So that's how we find the pressure that's in there. But depending on your diamond anvil cell design, you can get higher pressure.
never need more than 3,000 psi. So
3,000 psi. But there are other high pressure setups that give you lower pressures and more sample volume, which can be convenient.
perfect.
We're getting something
20 GPa.
okay. We need to
Gigapascals?
yeah, but that's for the pressure that you want. You might get away with the supercritical cell. I don't know how they compare. What's the maximum pressure in the supercritical cell we are getting?
Pascals.
300,
300 what?
300 bar.
Bars. So yeah, 1 atmosphere is 1 bar. How many did you want? Yeah, converting pressure units is all science. So yeah, no, serious. I get Google to do that for me. In the meanwhile, you had a question.
So did I hear you correctly that the IBM setup is open to users?
It is open to users. And I'll share the slides and you can email me. Yeah,
257 bars.
yes, you can do it. He said 300. Yeah. Yeah. Any questions? If not, you can check me again for the